So Jonathan Fay, standing right here, is the Dixon and Carroll Dole Executive Director of the Center for Entrepreneurship here at UMich, where he focuses on facilitating and inspiring entrepreneurship and innovation in PhDs, postdocs, and faculty here. So he came to the University of Michigan as a veteran startup executive from the medical device industry. He has led the development, regulatory approval, and launch of medical products ranging from infant hearing screening to asthma diagnostics to hearing devices. Most recently, Jonathan was the COO and CTO of EarLens Corporation. His responsibilities there included all R&D operations, clinical and regulatory activities. And in addition to his operational role, he was instrumental in raising capital from a variety of sources, including SBIRs, angels, strategic partners, and VCs, where he managed to raise $200 million to date. And in addition to all of that, he has over 16 patents and received his PhD in biomechanics from Stanford. Max Stein is a professor in material science and engineering here at the University of Michigan, and his group focuses on many things that we've heard about already, including hybrid materials for electronics, optoelectronics such as lighting, displays, photovoltaics, and thermal energy conversion devices. He's also an active entrepreneur and co-founded Arborlight, and is the author of Scalable Innovation, a guide for inventors, entrepreneurs, and IP professionals. Additionally, he has also developed a 2-semester multidisciplinary design course which teaches students the process of entrepreneurial innovation and technology commercialization through a hands-on approach.
With many of you, more on the sciencey type of stuff, the entrepreneurial thing is kind of like a thing I do outside my day job. So what's the point, and why all this talk about commercialization and patents and entrepreneurial activity when we're really trying to do science, right? National Science Foundation, not National Technology Foundation, not National Invention Foundation, not National Intellectual Property Foundation, National Science Foundation. Well, the problem is that a lot of us work on things that may or may not see the light of day, and oftentimes that's something that's a trade-off that you don't necessarily have to make. And it can be actually fairly easy to avoid making that trade-off, meaning the trade-off between something useful, something practical with commercial relevance, and something that's scientifically interesting and novel, right? So I don't know if those of you that have read Dr. Seuss when you were young, there's a sleep book and there's a line in there. A little passage says, "At the fork of a road in the valley of Abode, 5-foot weary salesmen have laid down their load, and they've raced round in the heat at top speeds, unsuccessfully trying to sell zizzers of seeds which nobody wants because nobody needs." And that's actually most of scientific research that goes on in this country. So we're basically going to talk to you about kind of saving some of the headache of realizing some years down the road that you did a bunch of stuff nobody really cared about. And not only nobody like in the real world, quote unquote, but not even scientists, not even fellow scientists read your papers and cite your papers. If you think about how long it takes you to publish a paper, it's about a year. And the amount of resources that go toward enabling you to do your research for a year is about $100,000. Okay, so a PhD is a $500,000 commitment that somebody has made to the taxpayers, namely, right? So $500,000 they've committed, you're doing something with that money, right? And then nobody even reads your paper, right? Now you think about how many citations you would, regard as a successful outcome of your scientific output. So that many papers that cite you, that means that many papers got written. You write about 1 paper a year, right? So that's how many 100K, increments have been spent that you also have to substantially enable, right? That you have to substantially have a hand in. So how do we avoid this kind of thing? So we want to know what people do care about, right? And what we care about may not be the same thing, but you want to find your community where people care about your stuff, and you want to make impact with your research, right? So the typical dichotomy that's brought up between impact factor and impact, right? Journals have impact factors, how many citations are made per paper and so on. We're really after both, okay? We're really after cracking that nut and providing both. And so part of that is thinking in a particular way and kind of keeping certain things at the front of your mind when you're doing your work and kind of doing your homework.
So how many of you have seen a graph like this? All right? How many have never seen a graph like this? Okay, so for those of you who haven't, I'll quickly go through it. So what you can kind of think of this is the amount of dollars that are available, right, the resources available, as a function of time and development, right? And at the very earliest stages, we're doing kind of really early what we call basic science research. We're not sure where it's going. We're trying to uncover basic scientific principles, right? And then as you go along, that's where academia normally sits. And then as you get over here toward commercialization, that's where industry and startups kind of really kick in. And the level of resources at a university is tiny compared to the level of resources available in industry. It's probably a factor of 100 or 1,000 different. Okay? So it's one. It's a log scale, right? And in between the two, there's something we call the valley of death, right? In between the two. And there's been so much talk about, how do we cross the valley of death? What's going on with the valley of death? We need more money for the valley of death. I got to be honest with you. More money won't help. It'll help a little. All right, fine. I'll give you that. It'll help a little. But really what the valley of death is, it's a valley of lack of information, right? This side over here doesn't know how to talk about their thing and do the right things. So this side over here, when it's starting to get ready, starts to pull, right? Because as soon as the industry starts to pull on something, additional resources get put in, and all of a sudden you actually have enough resources to actually move it along the scale. So really what we need to do is there's a lot of changes we need to make over here when we're doing basic science to make sure that when the discoveries are made, that the other side starts to see the value, starts to pull on it, and starts to put resources in. That's the only way we're going to change this kind of valley of death scenario. So I really want you to kind of think about, not think so much in terms of basic science and applied research, but think about it a different way. Anyone know where these two terms came from, by the way? No. Way earlier than that. Way earlier. Do you see the name at the top? Vannevar Bush. Anybody know who that person is? Anybody know who Vannevar Bush is? Who's Vannevar Bush?
Founder of NSF, or Dartmouth, right?
National Science Foundation. Founder of the National Science Foundation. Right after World War II. Okay? And do you know, he's the one that actually started this idea of basic research versus applied research. And do you know why he started those? Right after World War II? All right, so World War II is really the first time that the federal government invested heavily itself in basic science, right? And the reason was World War II was really the first electronic war, right? Where we really needed heavy science to maintain an edge and win. Okay, so it's really the first time. So we had this big kind of defense-oriented science complex, and now the war was over, right? Well, what are we going to do with this? And they really started to see that this investment they had made in these basic science and electronics and nuclear capabilities really had significant civilian applications and economic implications. So they wanted to keep doing it. So President Truman came to him and said, well, how do we describe it to people what academics are going to do, or what this kind of new National Science Foundation is going to do, versus what industry does today? And so they kind of made a kind of a Faustian bargain. Well, we'll call this stuff that academics do basic stuff, and we'll leave industry out so that industry doesn't get nervous that we're going to compete with them. Okay? So it was really out of that these terms came. Now, I don't want you guys to think in these terms, because I think it leads you down the wrong path. I think I want you guys to think about it in terms of this. All right? Rather than basic and applied, think about it in terms of search for fundamental understanding versus on one axis, and the other axis is consideration for use. Now we're going to play a little name game. Okay, so who's that? Anybody recognize that picture? Niels Bohr. That's right, Niels Bohr, right? Really high on the fundamental understanding. Not so high on the consideration for use part, right? Who's that? All right, that's Thomas Edison. He's the other way, right? Right? He, I think some of his Niels Bohr's famous quote is, everything we call real is made up of things that can't be regarded as real. Can you imagine him in a product development meeting? What is that guy talking about? Right? Who put him in charge? Okay? Right? On the other hand, we've got Thomas Edison. Right? If I can't sell it, don't want it. Right? Probably neither of those is the archetype we're going for. We're going for this guy. Right? Who's that guy? Yeah, Louis Pasteur. Okay? Who funded Louis Pasteur to do his work? Yeah, he did pasteurization, right? But who funded him? And why did they fund him?
University?
Okay, so who gave the university the money? Anybody know? Take a guess. The government of France. Okay? Why did the government of France fund his work? Yeah, okay, solution why? Why did they need a solution? What was the issue? What was the consideration for use? The French one was, oh my God, you got to solve this problem. Nope, not cholera. Okay, what does France make? What is its major economic at the time? Cheese. Yes, cheese. We make cheese. We sell cheese. We export cheese. We make lots of money off cheese. Our cheese industry has a huge problem. When we ship stuff, it spoils. Right? How do we make our product last longer so it can reach more markets and we can make more money and we get more tax revenue and we make this whole thing work? Huge, huge economic problem for France. Right? Similar to what we just talked about with NSF, we're at war. We have a huge problem that we need to solve. We have radar issues. The Germans are shooting down our planes. Right? Huge issues that need to be solved. Very high consideration for use, driven by a true, big, huge market need that drives the economy. Okay? So that's what we're looking for. Don't think in terms of basic and applied. Think in terms of how do I hit that past year's quadrant? How do I hit the deep fundamental understanding moving science forward that gets you your published papers, change in how the world works, and have a huge economic impact. That's what we're trying to figure out how to do. Okay? All right, that's past year's quadrant. All right, I'll hand it back to Max to talk about mousetraps.
Granted, we want to now, we're all on the same page, right, that we want to discover new science and we want to generate some kind of utility for the things that we invent, right? So now we're going to do something useful, and doing something useful in the realm of improvements, right? So actually you can patent improvements upon certain things, and that's considered as useful. Very famous saying there is, build a better mousetrap and the world will be a path to your door. And that's what most of us are doing. We come into a project and we say, well, people have done this thing, but it's kind of suboptimal, and can you make it a little bit better? So we kind of engage in doing that. Problem is that, the mousetrap you buy today in the store, the most common type, is over 100 years old. And people constantly try to invent a better mousetrap and build a better mousetrap, and it costs a lot of money to do that, but in the end, the thing that makes money has stabilized. And we call this, if you read the book, we call this dominant design. Once a dominant design has been established, there's not a whole lot of invention really to be done. And at the amount of money that we're spending here to invent a lot of the things that we're trying to invent in CellNet, for example, or that NSF would like you to invent, it's too expensive. Okay, and so if you're doing this, your chances of commercial success are very, very slim, close to zero, rounding off. And the chances that your paper will have a lasting impact is also pretty small. If all you're doing is getting the nth decimal place improvement in something. Commercially, it's a different story if you're an established company. But in terms of what we do at the university, it's a slightly different story, right? So we're not here to tell you that your research is good or bad, or to say your particular thing is going to be awesome. We're going to try to save years of frustration where, we've seen this happen. I've seen this happen as people, at the end of their 5 years, let's say plus minus, doing their PhD, come out like, why did I do this? I just had a tiny little impact in terms of what people know and understand now, and most of the time nobody even cares about it. 99% of patents are commercially useless. That's just a fact, right? And it costs an awful lot of money if you think about it. Now, on average, $25K per filing to do something like that. So this kind of approach, you build a better mousetrap and people are going to beat a path to your door is actually not quite true. So in the commercial realm, people have a lot of ideas, and ideas are quite cheap to come up with. And then as you go further and further down the path to implementation, the costs increase. But then the selection criteria get tougher and tougher. And so there's a huge amount of attrition that goes from the ideation stage down to patenting, down to actual implementation, down to actual sales, and then down to actual success in the marketplace. And the attrition rate you see is quite big. So when people say, oh, well, startups, 90% of all startups fail, that's actually very generous.
That's starting here on the graph.
It's actually a lot worse than that. And so, how do we, in the startup world, you always sort of wonder, how is it that your chances of success could be better than everybody else's, right? Because if you're realistic about it, why do you even start? But everybody who's in the startup scene thinks that they're exceptional. Well, are they? What is the thing that's going to allow you to succeed whereas other people don't? How do we increase our chances of success? And the same thing in science. There's just 1 million people doing science, and they're all really, really smart, right? So, what makes you think that you're going to be super awesome at it and awesomer than everybody else? How are you going to come up with that breakthrough first? And it turns out there's a lot of parallels between those two things, and there's certain methodologies that you can deploy to make your chances better.
Yeah, and I think that's where we really want to point out these parallels between kind of the typical startup world early on and actually what you're going to do in an academic lab. There are lots of things that are extremely similar. You're working in a small team is number one, right? You've got a different group of people around the table trying to work on different aspects of it, and you're trying to put that together into something that's going to have an impact. The other huge parallel is that both of them are an exercise of launching into the unknown, right? Can you publish a paper that's been published before? Well, I suppose you can, but it's generally not viewed as a breakthrough, right? Can you launch a product that's been launched before? Well, you can, but it's probably not going to be a huge success, right? So both a startup as well as an academic lab, you're trying to discover and move into the unknown. So actually one of the big programs I run, the National Science Foundation I-Corps program, is actually really about taking the scientific method and applying it to startups. So there's lots of parallels in terms of forming hypotheses, generating data, making decisions, and moving forward that you guys have been using in academic labs forever that actually work really well in startups. So not only is there similarities between startups and academic labs, there's also a lot of similarities between successful entrepreneurs and really successful academics, right? So everybody know who the guy on the right is? Steve Forrest, right? Probably the most successful entrepreneur inventor at the University of Michigan, possibly in its history. I don't know, maybe, maybe not. Close, right? Steve is always at the top of the list in terms of invention disclosures and patents filed, and I mean, he's been doing amazing things, and he's got some great buddies on the outside that help him commercialize that research, right? So what makes Steve really, really successful, right? Well, there's certain kind of behaviors that all entrepreneurs have, and hopefully everybody knows the lady on the right, or the left, right? Everybody know who that is, right? That's Oprah, right? Awesome entrepreneur. She's done amazing things in her life that have great impact on society. So kind of what are the behaviors that both of these people share, right? So there's what we call opportunism, right? They see opportunities to make a significant progress toward a larger goal, right? They understand what we call technology-enabled innovation. They understand this interplay between society and impact and new technology and new discoveries, right? In Steve's case, he's right on the edge with OLEDs and doing research there, whereas Oprah is really saying, okay, there's new technologies in sort of digital marketing. How does this affect my business? How does this affect my outreach? So really understanding the interplay between how society works and technology. Experimentation, right? Steve's obviously doing a lot of experiments, right, and testing things and willing to throw things out that don't work. Same with Oprah. She started lots of businesses. Not all of them were successful. Try new things. If it doesn't work out, move on, scrap them, right? If it's not working, kill it and move forward. Don't get stuck. Risk management, right? A lot of people talk about entrepreneurs in terms of risk tolerance or risk taking, right? How many of you have heard that? Okay, very popular. It's bullshit.
So for Oprah and Dr. Forrest. Oprah has been on TV. She has a lot of connections outside in the society. Dr. Forrest is also super famous. He has a lot of connections. For us being like PhD students and postdocs, like starting, what would be the most efficient way of looking at the society and then bringing it in? Because we don't have contacts continuously. So, for example, in my case, what I could have done is just worked with 2 surgeons to see the clinical need and then bring it in continuously. But the I-Corp that you mentioned, if you can expand on that, that would be also.
Okay.
And also.
Yeah, absolutely. That's an awesome question. You know why it's an awesome question? Because it leads into my next bullet point, right? Which is the #1 way that you can have an impact starting right now. Because again, to your point, you guys are not Oprah yet. Hopefully one of you will be, right, eventually. And you're not Steve Forrest yet. So the question is, when they were very, very early in their careers, what did they do, right? Probably the #1 thing they did was build relationships, network, get to know people, get to know a diverse group of people, okay? Don't just stay inside your scientific bubble. Get out there, meet people. And you know, the I-Corps program, that's honestly the foundation of that program, is to basically we take a group of scientists that all have their own kind of research and project, and we take them for 7 weeks, and we kick them in the butt and say, you're going to go talk to 100 people that are not in academic labs, right, related to your research. And simply the process of going around the globe talking to people that aren't scientists about what you do and doing it 100 times, you build tremendous relationships that you would have never built before. Right? And so I think that's the #1 thing that you can do. And then the other thing that happens in that program, along with building relationships, is you start to understand how to communicate, right, with people outside that scientific circle. Right? That is super critical in terms of being successful. Because here's the thing, right? If you want to write the great next grant that's going to get funded, it's a communication exercise. And you're likely communicating with a program officer at a federal agency that oversees an enormous portfolio and probably does not have specific scientific knowledge in the very detailed, narrow field that you're in. Okay? You should see the portfolios those guys manage. They're enormous and very broad. Okay? So, when you present to them, you need to have really good communication about why your science is important, and that will definitely make you stand out. What you're really trying to get them to talk about is, what are their issues? What are their problems, right? What would they pay for, right? Or what's the pain that they're feeling at the moment? Because people, if you ask them straight out, what do you want? They go like 1 degree off what they have today, okay? Or if you ask, what are you struggling with? What are your fears? What's causing you to lose sleep at night? What gives you frustration in your work? They can articulate that, right? And that gives you that kernel you need to start going forward and figuring out if you can solve their problem or not. Absolutely, great point. And then the last thing that these 2 people have is perseverance, right? No entrepreneur and no academic will tell you that you don't need perseverance, right? A lot of, again, back to the popular literature, a lot of people will use the word passion. I actually don't like the word passion because I think it gets misused. The real word, in my view, is perseverance. It's going to work, working hard, working 10, 12 hours a day when it isn't fun anymore, right? That's when you actually have true passion for something, when you're willing to push through, do that hard work, keep after it, have the energy to do it, and eventually, after a long period of time, you'll have success. So it's really about perseverance.
I've worked with Steve for many years. I've known him since 1997. And I've seen him work. Let me tell you, he works a lot. He worked harder than anybody else. And I remember how hard I worked, or at least I thought I worked hard. So this thing about putting in the hours, again, it's not an either or. You could work smarter, people say, or you could work harder. We're not talking about either or. If you're really trying to make impact, you can't do without both of those.
So let's think about an academic lab as a startup, right? That's the new frame we're going to try to get our minds in. So what are the products of an academic lab? Right? I've listed probably the top 3. Actually, I probably should have perhaps reversed the first 2, right? Students, publications, and then patents, right? You've heard a lot about patents, but let's be honest, patents are probably a distant third to the other two, right? This is what academia does, right? We publish, we graduate students, okay? Who's the customer, all right? So for publications, it's other academic researchers and the funding agencies, okay? For the students, it's mostly industry and a little bit other academia. I'm just curious, how many of you want to go on to have academic jobs? How many don't know? Okay, raise your hand high. Okay, good. How many of you do want academic jobs? All right, a few, okay. So most of you think you're going to end up in probably industry or somewhere else, right? It is about a 95-9 split, 5 split, by the way, in terms of PhDs graduating and where they go. And then the patents, as you heard Bryce talk about, 95% of all inventions and patents out of academia just get licensed straight into a big company, okay? And 5% go on to be startups, or maybe even smaller, okay? All right. So as we're approaching this valley of death and crossing it, it's a multi-step process. So we're going to start with the basics, all right? So I pulled this off of CellMet's website, and this is kind of the midterm goal, right? To fabricate personalized heart tissue that could be used in the short term to test the efficacy of drugs and eventually to replace diseased or damaged muscle after heart attack, all right? And so the key question here is, what is CellMet's business?
So we're in business. And what kind of business are we in, according to this? We're in the business of fabricating stuff, right? And we're very, very good at this stuff, at least as good as anybody else in the world, right? That's the idea. That's why we got the money. That's why we brought you in here. Strict admissions criteria. Okay, so we're going to fabricate. We're fabricators. What are we fabricating? Well, ultimately, it's some kind of heart tissue. It's personalized heart tissue, not just any heart tissue. That tissue's got to be, right for each person that's going to use it. Yeah. So that's the unique quality of the product that we're ultimately trying to make. And then there's this phrase in there that says, "to be used." Are you going to put it in? Probably not. Is your lab mate going to put it in? Probably not. How many steps, stages does it have to go through before the thing that you make in the lab and that little scaffold actually gets put in? Right? So the question is, who's putting it in? Who's using it? At what point? Well, we say in the short term, okay, that's the long term, forget about that. In the short term, it could be used to test drugs. What does a drug test involve? Do they just give it to people that are volunteers and see what happens? Do they give it to the animals and ask them how they feel? What happens before it gets to the animal, right? So many of you actually know the answer to that question. Really, what's that process? And why does it take $2.5 billion from discovery to actual use in the market for a drug? A single drug, from the discovery to market, $2.5 billion. Okay, I haven't got that kind of money. Not yet. So, okay, we're testing drugs. Which drugs?
All of them are,
Right? So pretty much, every drug you put in can affect the heart. So oh my gosh, that's a lot of billions, right? There's a lot of compounds out there being used for all kinds of stuff. So there's a need. Again, replacing diseased muscle tissue afterwards and so on and so forth. So this is the overall, you guys have seen this even with higher quality than shown here, so you can actually read all of where you are. So you need to be able to locate yourself in this thing, right? And then figure out how information is going to flow and how your output is going to enable somebody else in the center to do the thing that they're trying to do, right? So actually, even within the center, you have a system of products that you're producing that are getting used by other people whom you can regard as your customers. And are you giving them what they really need and what they could really use? And how much are they paying you for the stuff that they're using? Well, so there's an analogy in system design. This is typical engineering system design beat, it's called the system design beat. How many of you have seen this before? Some, maybe. Okay, so this is developed by the aerospace industry and used by lots of other industries, if you're putting together complex systems, which these heart tissues are going to have to be, right? And this entire center is this complex system. You have this sequence of customers, okay, and vendors and suppliers. And up top is somebody that says, I need heart tissue. And then below it, somebody that says, oh, here's heart tissue. And then, but they're like, well, I built it out of the following components, right? And so you've got your systems that comprise the final product that you're selling, and that consists of components and subcomponents all the way down to the materials and the molecules and the polymers that you're going to use for the scaffold or to encourage cells to bind to specific sites, differentiate into the right things, and so on and so forth, right? So, and every time, so we on the material side of things, or we on the scaffold side of things, have to ask the question to somebody who sits above us on this hierarchy, not because they're better people than us, but just that they're our customers. And we say, what is it that you need from us? And then they in turn have to ask somebody above them on that flow chart, what do you need? Right? So you have to visualize this thing, and of course it's a recursive process, and you have to kind of loop through it on many levels, many times. But you've got customers, okay? In the CellMed Center, you've got customers. What do they need